Okay, hello. I am Hanne Baeke, a PhD student at KU Leuven in the group of Giovanni Lapenta. And I will tell you about the work that I've been doing on the classification of solar active regions with clustering techniques. The previous talk was actually a good explanation of a lot of the concepts that I used. But as a recap, solar active regions are regions on the sun where the magnetic field is locally more intense, and they are often the regions of origins of solar flares. And these solar flares can pose radiation hazards to astronauts and spacecrafts, and at extreme strength they could knock out our electrical power grid here at Earth, which is why we study them. The main research questions that I tackled are whether it is possible to classify solar active regions based only on their magnetic field parameters, and whether there is a relation with this classification with the simultaneous occurrence and the strength of solar flares. There already exists a lot of sunspot classifications. The Mount Wilson and the Macintosh ones are the most widely known and used, but they are both performed manually and they are based on the morphology of sunspots. And because they are still performed manually, they can sometimes be quite ambiguous, and therefore there is need for a more automatic and objective classification. There's also already been a lot of research on that, but I try to do that by using unsupervised and supervised machine learning methods. And I based my methods not on the morphology of active regions, but on their magnetic field parameters. The magnetic field parameters that I used are simple, single-valued measures of the active regions. They are integrated over the relevant area, so inside the contours of the active region and where the magnetic field is above a certain threshold. As a data set, I used one created by Engrick et al. This includes 24 different magnetic field parameters. 16 of them are sharp parameters, and then there are also 8 additional ones that they created themselves. What is also included in their data sets are, for each active regions, the type of solar flares and the amount of this type of solar flares that occur at the same time. These solar flares are intense brightenings at a small area on the sun, and they release a lot of energy. And they are categorized according to their X-ray flux, where we have X flares at the strongest flares, then M flares, C flares, B flares, and A flares. Those B and A flares are often so weak that it's hard to distinguish them compared to the background radiation. Therefore, I merged the active regions with B and A flares together with active regions that show no signs of flares, and I will refer to those as non-flaring active regions as a whole. Then the rate of occurrence of a certain type of flare is inversely proportional to the strength of a flare, which is why the data set is largely imbalanced. You can see I have a lot more non-flaring active regions than active regions that show X flares or M flares. And therefore, I performed 2 sampling steps. First, I randomly undersampled the non-flaring active regions to 50,000 samples. Why this amount? Because this was really the amount of data that I needed to keep in order for the processing steps that I will explain in a minute to perform well. But you can see the distribution is still very skewed, which is why I performed a second sampling step. This sampling step I performed after all the processing steps, but just right before the actual classification of the active regions. I randomly undersampled the majority classes, so the active regions without signs of flares and the active regions with C flares. And then I oversampled the minority classes, so the active regions with X and M flares. And for this, I used a smooth oversampling technique. So then I started with the processing of the data. First, I removed outliers. For this, I used a clustering technique called HDB scan. And all the data that did not belong to a cluster is assigned as outliers. I show the distribution of two magnetic field parameters before and after outlier removal. And you can see that the general distribution of the data was not very clear when there were still outliers. Afterwards, it's a lot clearer distribution. And then on the right, I show an example of such an outlier. In this case, the spacecraft was rotating or repositioning while the measurement was taken. So yeah, those types of outliers really need to be removed. Then I noticed that there was a lot of redundancy in the data sets, as was also explained in the previous talk already. I show here a covariance matrix, and you see that there are a lot of dark blue squares, which shows that a lot of these magnetic parameters are related to each other. And I eliminated this redundancy with an algorithm called common factor analysis. And this algorithm looks for the factors that are common to multiple parameters at the same time. And I found that actually 5 factors were sufficient to cover all the data. And this is how each of the 5 factors is related to each of the 24 magnetic field parameters. As a next and last processing step, I again made a higher dimensional representation of the data set. I went from 5 dimensions to 7 dimensions. Why did I do this? Because I wanted a hyperplane where the spread between the data was maximal. For this, I used a sparse autoencoder. This is a type of neural network where the target values are set equal to the input values. And yeah, I show here the architecture that I used. You can see that the number of hidden nodes is larger than the number of inputs and output nodes. So you could think that this algorithm would just learn the identity function. But that's not true, because a sparse autoencoder has as a constraint that only part of the hidden nodes can be active at the same time, or in other words, only part of the nodes can have a non-zero value at the same time. And this creates sparsity in the data sets. This constraint is made sure of by adding an L1 regularization term to the loss function. And this regularization term is applied to the activation values of the hidden nodes. So then, as a final data set, I used the learned values inside the hidden nodes, which is a higher dimensional representation of the original 5 parameters. So then my data was ready to be classified. First, I used a supervised algorithm, k-nearest neighbors. This is supervised, so I used the flare labels connected to each active regions as the labels for the algorithm. I show here the confusion matrix with results. As you can see here, almost all the X flares are always correctly identified. But as a note, I also largely oversampled the X flares, so this is a bit too optimistic. I try to eliminate this influence as much as possible by using cross-validation, but still it's a bit too good to be true. And then I found that the C flares were the hardest to distinguish, with only half of them correctly identified. This is because the distribution of their magnetic field parameters overlaps with the distribution of the magnetic field parameters of M flares and non-flaring active regions. And you can see that almost 30% of the C flares is misclassified as an M flare. This is partly due to the overlapping of the distributions, but also because I oversampled the M flares.
5 minutes.
And then afterwards, I also used an unsupervised method called k-means. This is unsupervised, so I did not use the flare types as labels at all, but I did use the flare types afterwards to analyze the results. And this is what this figure here is. In this figure, I show the percentage of each type of flare that is present in each cluster that I found with k-means. You can see here that in cluster 3, this cluster 3 covers about 66% of the non-flaring active regions. And then I found that cluster 2 covers about 40% of all the flaring active regions, and only 7% of the non-flaring active regions. So this cluster is, to some limits, able to distinguish flaring active regions from non-flaring active regions. However, to distinguish between the different types of flares is a lot harder because they all occur with about the same percentage. What we can do is to look at the probabilities to belong to different clusters at the same time. For example, in cluster 4, there are twice as many X flares than there are C and M flares. So if you would have an active region that has a high probability to belong to cluster 2 and to cluster 4, it is more probable to be an X flare. The difficulty of distinguishing between active regions with different types of flares is a problem kind of inherent to the data. In this figure, I show the mean and standard deviation of each of these 7 parameters for each type of flare. And you can see that the mean for non-flaring active regions is quite different from the mean of flaring active regions, but between the different flaring active regions, the differences are not that large. What we could do to make this more distinguishable is to maybe discard non-flaring active regions or active regions with weak flares and to only look at C versus M versus X flares, because then these small differences will become more significant. So then to conclude with our method, we find that flaring active regions are distinguishable from non-flaring active regions. We also see that X flares differ from C and M flares, but to really distinguish them, it would need some more analysis. And then we find that the magnetic properties of C and M flares are very similar, which is a problem inherent to the data sets, or at least as we now used it. Then another explanation of why this is difficult is because the solar flare classes are artificially defined. We try to distinguish C flares from M flares, for example, but a strong C flare will be very similar to a weak M flare. So it will be more easy to try to distinguish weak flares from strong flares than to really find all the M flares. And then for future work, I would use time series instead of single time points, and combine this data with other data like images of the active regions, or other features like, for example, the maximum flux in an active region. Yeah, okay, thank you for your attention. If there are any questions.
Thank you very much. Are there any questions in the audience, Piers? Then Manolis.
That was really interesting, thank you. You mentioned it there just right at the end about how a strong C-class flare is very similar to a weak M-class flare and all the way up. But have you or any other people tried to classify flares within like C1, C2, C3 at that sort of granularity, or is that too particular?
No, not yet. But yeah, that will be more difficult, I think. Yeah.
Good, thank you.
So thank you, that was interesting. Let's see, you tried both a supervised and an unsupervised method. So your preliminary conclusion would be that supervised methods work better than unsupervised one, or vice versa?
Well, it depends what you want to do with it. If you want to find active regions where M flares occur, then I think the supervised one would work better because you have labels, while with the unsupervised method you're actually not looking for that, because you just try to find clusters of active regions that are distinct, but that doesn't really have to do anything with the type of flares that come out from. But that is what we looked for. So if you want to look for that, I think supervised would be better. However, unsupervised would be better for production purposes because you won't always have the types of flares available, especially if you want to find them from the active regions.
Right. And then you mentioned that a high C-class flare is going to be very similar to a low M-class flare, which I agree with. It is not really an artificial definition. It's just a change of the order of magnitude in the peak photon flux. But we do not necessarily need to be able to come to that level of detail as to identify active regions that will give us a C9 or an M1. What one could do is that one could skip a flare class. Let's say one could try to identify active regions with A or B's, so non-flaring ones, versus active regions of M and above flares.
Yeah.
So in this respect, things might be coming more clear, perhaps. And there is also a space weather forecasting significance because we do not necessarily care about the smaller flares, we care about those flares that have a potential of giving us an eruption. Have you tried that?
I haven't tried it, but
okay.
I agree that it's a good method and it will be easier if you discard the C flares and then distinguish between the weak and the stronger flares. Yeah.
So you might be able to clear the fog in this way.
Thank you.
Thank you. Any more questions in the audience here? Yes.
Hi, that was a really good talk. I was just wondering, have you also tried reducing the dimensionality of the data? I missed if you said this or not.
That's what I did with the common factor analysis.
Okay.
So here I went from 24 parameters to 5 parameters.
Yeah, okay. Do you think there's anything sort of meaningful that might have been lost in that's causing the sort of disparity in the M and C class pairs being?
Information that's lost?
Yeah, do you think there's anything that might be significant enough that could be missed? Or?
Yeah, I'm not entirely sure, but I don't think so. I think I kept 5 factors, and I think that covers about 99% of the information that was in the original data sets. So.
Okay, thank you.
Thank you. Any more questions? I have a quick question. So first you mentioned using HDB scan and then k-means. So why did you choose one then the other and not just stick with, for example, HDB scan, which seems to be performing in general better than k-means?
Yeah, it's because my original plan was to use k-means, and then also because k-means includes all the data points, while HDB scan finds clusters, but all the data points that do not really belong to any cluster, they discard. So that's why I used it to find the outliers, all the data points that I could not really assign to a clear cluster. But yeah, I do think that HGB scan could also work for the later classification itself. Yeah.
Thank you. Oh, one more question, Francesco.
Hi, thanks for the talk. It was really interesting. I wanted to know about the confusion metrics that you showed with the supervised approach. Since that you say that your result seems too good, did you try to check if, for example, for the X detection, you could detect the true X flares instead of the fake generated by this mode technique?
I did, and then the results are indeed a lot worse.
In which order of magnitude?
Yeah, I think like maybe 60%. So yeah, still okay. Yeah.
Okay, thanks.
There is a question online if there is time.
Yep.
Milo, go ahead. Yeah.
Yes. So nice talk. You mentioned at the beginning that right now we have a couple of catalogs with the human intervention. And what you have showed looks very powerful. So I'm wondering how far are you to have something that is a tool available for a classification entirely with a non-human intervention. That's one. And two, having probably a probability for a certain active region to have a flare or of certain ghost classification in the forthcoming future.
Yeah, so your question is
Yeah,
how far
the
I
question
am.
is how far are you from having a tool publicly available that gives you a new classification where the human doesn't intervene and maybe give you a probability that that particular active region that you see on the solar disk is going to have a flare of any kind?
I don't think far enough. Because, yeah, especially if I would want to use it for production purposes, I would want the unsupervised classification methods to work well enough, and that is not the case right now. Yeah, because you really have to look at different clusters at the same time, and then still it's with a certain amount of uncertainty that it could be a certain type of flare. But yeah, I don't think the probability is high enough already.
Okay, sounds good. But thank you. It's a good tool.
Thank you.
Thank you. Any more online questions? If not, let's thank our speaker again. Thank you very much.